Good afternoon, everybody. We'll get started in just a few minutes. Thanks for your patience. Okay, so it's right at 5. So I'm going to go ahead and get started. I'd like to start our session today by opening up the floor for any questions that you might have regarding last week's material so that we can close that chapter and move on to the next topic for discussion. So any questions, feel free, unmute, ask your question.
Is the project included in that to ask questions or no?
Of course, sure.
Um, the only question I had was for the project. I know you had the little website part that we needed to go to look up the articles. Um, what kind of articles did you want to be exact? I know it was 15 pages. It had to be 15 pages plus, and you wanted a summary. But what titles are you looking for? Like, what kind of article to be exact?
Okay, so I'm going to share my screen to help answer that question.
Okay.
All right. So tell me if you can see the screen.
Yes.
Okay, so if you click on assignments and activities, that's the quickest way to get to the project. You can get through to it under the syllabus or in the weekly overviews, but I always just click on assignments and activities because I know under that tab, all of the various assignment categories are explained. So it's being a little bit slow here, so just bear with me. As soon as it comes up, we'll go in and take a look at the project again, just to make sure we're all on the same page. So thanks, Amanda, for asking that question.
No problem.
All right. So if you noticed, I clicked on project, and then right in the project details, the very first link, if you begin reading under directions, it tells you the 5 topic areas: astronomy, mechanics, which is motion, energy, waves, or thermodynamics. So any article that you use has to be related to one of those 5 broad categories or broad topic areas. And you mentioned the website. I suspect you're talking about the Hindawi website, which is
Yes.
definitely fair game for finding an article, but that article has to be related to one of these 5 topic areas.
So when I go to the website, I just go to the top and just click in one of the like the titles for astronomy or mechanics or anything like that, and then whatever one pops up, I could just look at it from there. Correct?
That's correct. You'll use the search feature. That's probably the easiest way to do it. Is just go in the search feature, type in the topic area that you're looking for, and then begin, going through those articles to make sure that they are long enough, connect, that they're science oriented, because, there are articles on Hindawi that have like a more um, engineering or economics kind of feel to them, and that's
Mm.
not where I want you to focus. So something that's more science oriented regarding these five topic areas. I tell students that if you find an article that's related to one of these that's typically doing some type of experiment, then you're kind of on the right track there. Okay.
Okay. Um, and how are we sending? Are we sending the whole article to you? Or are we sending? What are we exactly sending to you for you to
Yeah.
approve for us to do that article?
Right here. So see right here, it tells you to get your article approved. You email me the full PDF, right? It says, please attach the full article as a PDF file and email it to me.
Okay.
Yeah.
Alrighty then. I think that's about it for me. Everything else is pretty much self-explanatory at this point.
So this is why I want to give, some time for students to find the article. That's why you have a deadline of the 26th of June. And so after that, then we can get more into the writing, right? Right now, the focus is finding an article, which does take some time. Um, and then you can start the preliminary reading of the article, and we'll start to talk about, okay, now that you found an article, you're reading the article, noting the things that are important,
I have a
how it
question.
connects to the class. We can talk about how you put your summary together, but we'll do that later on, not right now, because I suspect that there are still many students in this course that are looking for an article.
Okay.
All right. So that's that.
I have a question,
Yes,
Matthew.
yes, please.
Can the article be one article or more than one?
The article for this class is only one article. If you are in lecture and lab, then you have to have
Thank
two
you.
separate articles because you're doing two separate projects. But if you're doing the project just for this class, it's a single article that you're looking for on one of these five topics,
Thank you.
15 pages long, science focused, right? Does that help?
Yes, it does.
Oh, okay, great, great. Anybody else? All right. So thanks for the question. So what I'm going to do is go into the weekly overviews now. I got like lots of emails this weekend from students in both classes asking me where to find the assignments and where do I find something to help me with this assignment. And so I remind you that the weekly overviews are where you find information on what we're covering for the week, the activities that you have to do for the week, along with the links to the actual assignments and materials that relate to the topic area, readings from the textbook, videos, so on and so forth. Okay. So, um, you know, I'm not quite sure what the confusion was. Maybe it's because this weekend was the first time you had to really dig into the physical science of the course. But the weekly overviews, I can't stress that enough. If you aren't going there to find the materials and the assignments, you're probably looking in the wrong place. Okay, so just be aware of that. All right. So with that being said, then that's exactly what I want to do. I want to go into this week's materials. Okay. So you see here, week 3. God, it's week 3 already. Goodness gracious, it's flying by. So you see here that there are 3 topic areas that we're going to focus on. So we're going to begin our study of motion. So we're going to be looking at one-dimensional motion. I just abbreviated it as 1D motion. We're going to be looking at vectors, and I'll briefly mention this concept of vectors today as well. But and then I'll talk more about this vectors overview on Wednesday. And then on Wednesday, we'll do the 2D motion overview as well. So I want to focus on 1D motion today. Uh, I'll briefly mention vectors. We'll finish up with vectors on Wednesday and do 2D motion on Wednesday. So everybody clear on where we're going this week? Okay. All right. So let me go into that overview. So as I mentioned, we're going to be looking at motion. We're starting our study of motion. So let me make the connection between last week's stuff on how we do things in science and measurement, in particular measurement, right? Because now what we're going to be doing is using the concepts that we came across regarding measurement to help us describe, quantitatively describe a moving object. So we're going to be relying on our understanding of this idea of a quantity or a property. And we're going to be relying on our understanding of measurements and units so that we can then describe an object that is in motion. And that's a big part of what we have to do in this course. That's a big part of what this course is about. What kinds of things do we need to explain when we want to quantitatively, through measurement, describe a moving object? So you see the objectives for this topic area. So we're going to be talking about what kinds of things are required if we're going to be, if to establish that an object is moving, right? If our goal is to describe a moving object, then we have to know what defines motion, right? What does it mean that the object is in motion? We're going to be looking at properties like position, speed, velocity, and acceleration. You'll look at property distance and how you find distance. We'll look at relationships between position, velocity, and acceleration for an object in motion. And this objective will also carry over into the lab class. We're going to be doing that, an experiment that directly relates to this objective in our lab class. You'll look at motion graphs. In fact, I have a really nice video that I'm going to be sharing with you so that you can begin to understand how we use graphs to describe motion. And of course, we can't divorce ourselves from the fact that we need to be able to calculate, solve problems regarding these topics. And so we're going to be utilizing the kinematic equations, and I'll explain what all that is when we get to it, but you'll be utilizing them to help you do some simple kinds of calculations. And then we'll look at this idea of free fall, and you'll be solving free fall problems. Okay. So that's the kinds of things you want to be able to deal with from this topic of 1D motion. Now, let me also say this topic of 1D motion is fundamental because the concepts and the properties that we study when we want to describe an object that's moving in one dimension are the same types of properties that we want to utilize to describe objects that are exhibiting other types of motion. Okay, so this is like the basics. This is the foundation for being able to deal with motion. All right. So you see you have some activities on your plate by Saturday. So the 1D motion discussion is due by Saturday. and you know the rules for that. You go in, you post your answers to the questions, and then you reply to two of your classmates. I was quite shocked when I scored the discussions from this past Saturday that lots of students did not do the discussion that related to the nature of science and measurement. You're shooting yourself in the foot if you're not doing these discussions. Okay, so you know, if you aren't doing them, you need to make it a habit of getting those done. And for those of you who are doing them, great, keep at it. Right, the goal is for you to have dialogue with your peers about these topics, much like you would if you're working face to face. All right. Problem set number two, which is due Saturday, is actually dealing with measurement, right? Because remember, problem says lag a class period behind, right? So a topic behind. So we dealt with a measurement last week. The problem set two focuses on that aspect of measurement that we dealt with last week, things like unit conversions. Okay. All right. If you're looking for instructions on how to turn things into me, right there in the weekly overviews, you have it available. And don't forget, you can always drop a question in the class questions forum, but probably the quickest way to reach me, and most of you figured it out by now, is through email. Okay. So here are the items that can help you with this topic. Okay. So I've marked for you the portion of our textbook chapter 3 that deals with 1D motion. You should go and read that and come back to me with your questions if you have them, or bring up your questions in the class question forum, or even you could say, hey, look, I was reading a textbook and I'm not too sure about that. Write in the discussion forum. Don't hesitate. All right. There's some videos on 1D motion and free fall. And then we're going to watch this motion graph videos here shortly. But what I want to go into now are my notes, the supplemental kinematics notes. Okay. So I'll remind you, these are all the kinds of things that you should be doing in your quest to understand this material. You have to do your due diligence. This stuff that we're learning only comes through practice, right? I mean, you know, you just have to get down in the muck with it and practice, right? And ask questions. Okay, so these are the things we'll focus on in this packet. And those are much like the same objectives that you saw on the in the weekly overview. All right, so let's get into our study of motion. All right. So I use that word kinematics. I said that we're going to be looking at the kinematic equations. That word kinematics means motion, but more specifically, it means motion without considering the cause for the motion. So the object is moving and we want to describe it. We don't care what made it move. We don't care why it's in motion or what caused it to be in motion. We just want to describe the actual motion for that object. Okay. And so, for example, they gave you the example of the birds in flight. So kinematics describes how it turns, rises, and descends without regard to factors responsible for the bird's motion, such as lift or wind or gravity, right? So kinematics is pure motion. We don't worry about the cause. We'll get to the causes, but right now, we just want to be able to say that thing is moving. Let me tell you something about that motion, okay? And we'll look at the kinds of things that we need to be explaining to describe that moving object, okay? Now, true enough, you know, we live in a 3D world, but we don't try to describe the motion from a 3D perspective. In here, we look at the motion from the perspective of one or two dimensions at most. You know, if you want to think math, X and Y. Okay. Some of you may have been in a class where you did a graph or You know, you did graphs for me if you were in lab this past week, and that you had that X and that Y, the horizontal and vertical, 2 dimensions. But what we're going to do to get started is even make it more simple than that. We're going to focus on just 1 dimension. Okay. So think of it, the object can move um, left or right, up or down. Okay. Um, Forwards or backwards. Uh, we want to keep it simple to get started here. Okay. So we confine our motion to 1 dimension. And what kinds of things do we have to, um, express or explain when we want to quantitatively describe an object in motion? In other words, another way of saying that is, what properties of the moving object do we measure when we deal with kinematics? Okay. So position, displacement, time, velocity, acceleration. Those are all examples of properties of our moving object. So position, for example, tells us where our object is located. We can measure that. Displacement, we'll see the definition here in just a moment, helps us to understand how the object is moving in reference to where it started. And that can be measured. Time, how long is it taking the object to go from one place to another? We can measure that. And velocity and acceleration. So, and then there are other properties as well, speed and distance. Um, those are also properties that we can measure that help us to kinematically explain the motion of our object. Okay. There's another important parameter that we have to utilize. And you can see by now that we borrow a great many things from the Greeks to help us, including their alphabet or their letters. So the Greek letter delta is utilized to represent change. So obviously, if an object is in motion, there are things that are changing, and we can use that letter delta to represent change. And the way it works is that whatever the delta symbol is in front of, that's the property or parameter that's changing. So if I write delta t, that means a change in time. Okay. So we have to, the notation is involved, right? I mean, we all have to make sure that we're communicating and speaking the same language when we describe our moving object. So we got to understand common terminology, and delta is one of those um, symbols that we utilize to help us explain the motion of our object. Another very important property is the position, right? So we can locate an object by specifying its position, all right? But as I said, all of these properties, including position, are something that we measure. So to establish that position, to establish the object's location, we measure. And so, we have to measure with respect to a reference frame. Okay. So let me try to give you an example beyond what's given here to help you understand this concept of reference frame. So if I ask the question, okay, you're sitting at home, you're sitting in front of your computer, or you're, sitting on the couch with your iPad and following along. If I asked you, hey, is your computer moving, or your iPad, is it moving? And so if you think about that carefully, you have to ask the question, With respect to what? What do you mean? Is it moving? Is it moving with respect to the room that I'm in? Is it moving with respect to the earth? Is it moving with respect to the moon? Where are you measuring from? What is your reference point? Okay. So clearly, if you think about that question, with respect to the earth, your computer is not moving, right? But if your reference point, if your reference frame is the moon and you're looking down on the computer from the moon, clearly you'll see that it's moving. So it is important it is important for us to clearly establish a reference point or a reference frame so that we can properly describe our moving object and establish motion. Okay. So I like the picture that they give here, because what we want to do is we want to choose our reference frame or reference point for convenience, right? And so, for example, they said the Earth is typically used as the reference frame for an airplane. So if you're standing on the ground on Earth, looking up at the plane, you'll say it's moving. But if you're riding in the plane, if you're using the airplane as your reference frame, then as a passenger, the plane is moving, but you are also moving if you're in the plane. So according to you, um, the plane, you would say that the plane is not in motion, right? It's kind of like we're on the Earth. The Earth is whizzing through space, but according to us, we don't feel that. We don't see that. Okay. So, a key property that we have to establish when we describe moving objects is position. And in order to establish the object's location, we need a reference point or a reference frame to measure from. Okay. Displacement. So displacement helps us to look at how the object is changing its position. So once we've established where the object is located, then we can establish the change in that object's location or the change in that object's position. And so that's how we define displacement. Be careful. There's a related property called distance that also utilizes the idea of where the object is located, but the distance is looking at just how far the object moves along its path of motion, right? So they give the example there. They have home and they have a store. So if someone started at home and they went directly to the store, they would have a distance of 3 kilometers. And you would say displacement, you have to be careful. You would say the object moved 3 kilometers left, right from its starting position, right? But to clarify the difference between distance and displacement, if the person went from home to the store and then back home, they would have traveled a distance of 6 kilometers. But their displacement would be 0. Why? Because the displacement looks at how the object changes its position relative to where it started. And if you end up where you started, then, hey, your position hadn't changed. But if you go from the home to the store and back, you definitely have a distance. So this highlights the difference between those two important properties. So you see, if we're going to describe the moving object, if we're going to describe the motion of the individual that's going from home to the store and then back, we have to be very specific. Because if somebody said, well, describe that moving object, well, what do you want to know? Do you want to know how far they travel, which is the distance? Or do you want to know how far they are relative to their starting point, displacement? Okay, so be careful that you are explaining the property that is being asked for when you you know, describe a moving object. And I know that terminology is a little bit, you know, like it's a different way of thinking, because when we say describe something, typically we're talking about how tall is it, the color, you know, did they have on red shoes or green shoes? But in this case, when we say describe a moving object, we're talking about these fundamental properties that help us in our kinematic description of the object. All right. So now I explained to you what displacement is and what distance is. The question then becomes, how do we actually calculate it, right? Now, distance is very easy to calculate. You just follow the object around and measure how far it's going all the while that it's in motion. Okay, so you measure the path that the object took to get to how far. But to get the object's displacement, the change in the object's position, you use the symbol delta x. Delta x, change in position. So we're using x to represent position and delta x to represent a change in position or displacement. And the way we get delta x is we take the final position minus the starting position. So in this formula, delta x equals x final minus x naught. This might be a new way of terminology here, this subscript 0. So what we say is x naught, or the initial position, okay? Sometimes you see that used because they're trying to signify the position when the clock was at 0. So we say the final position, x with the subscript f, minus the starting position, x with the subscript 0. So x final minus x naught. Naught, that is a term that means nothing. When the clock was at nothing is literally what it's saying, okay? But the easy way to think of it is this: take the final position minus the starting position, okay? All right. So they give an example here. It says, if an object moves from an initial position of 2 to a final position of 7 in a reference frame, then its displacement is 7 minus 2, or 5. For the reverse situation, this is very important here, because when you're finding displacement, you have to be careful, because it says x final minus x initial. Whatever that happens to be, that's how you do the subtraction, okay? In other words, you don't always have the bigger number in front when you subtract, okay? So it says, for the reverse situation, where the object moves from a position 7 to 2, meaning the starting position was 7 and the final position was 2, then the displacement is 2 minus 7, or minus 5. And typically when you're doing these, because you're doing a position, you're dealing with a measurement, there'll be a unit involved. But they didn't put a unit because it's kind of a generic, right? Whatever unit you're using. If that happens to be meters, then your unit is meters. If it happens to be kilometers, then your unit is kilometers. You know, whatever your unit is what you will include with the actual numerical value. Okay. Now, they say here, this illustrates that displacement has both magnitude and direction. Magnitude and direction. Magnitude means the number, the size. That's vector language, magnitude or size. What is the size of this displacement? 5, because that is the number part. This negative sign is what tells you the direction. Okay. All right. And we'll look at that just a little bit more here shortly. But I'm highlighting something very important for you, that this displacement property can be positive or negative. Whereas distance, which is how far the object moves, can't be negative. Okay. This negative sign is meant to indicate direction. Okay. So we typically say that to the right is positive, to the left is negative. And so we know from this displacement -5 that the object stopped 5 units to the left of wherever it started. Okay. That's just a brief introduction to this idea of a property like displacement that can be positive or negative. All right, and we'll look at that more in more detail, especially when we talk about vectors. Okay. Now the unit, because I did say that typically these calculations finding delta x will have a unit associated with it. And last week I hopped on the idea that in the metric system, we focus on our SI base units, right? Our base properties. And so the SI unit for displacement in our metric system is the meter, because that's how we measure this displacement, utilizing the unit meter. So we could say, for example, here, if the object moves from a position of 7 meters to 2 meters, then its displacement is -5 meters, because we'd have to have a unit on there. Okay. Notice carefully that the property distance, which simply tells us how far the object moved, is also measured in meters. So you have to be careful. You have to be careful. Do you want the property distance or do you want the property displacement? They're both measured in meters, but you find them very differently. Okay. So here we go again, scalar and vector quantities. This is a brief introduction, and you'll actually have the opportunity to work through the vectors overview, and I'll talk more about that on Wednesday. Okay, but this is just an introduction to get you thinking about, hey, these are the kinds of properties that we measure, and some of them are scalars and some are vectors. Okay, so a scalar property, a scalar quantity, is any quantity. Remember, a quantity is something that can be measured. Okay. A scalar is any quantity that can be measured that has a magnitude but no direction. A magnitude is simply a positive or negative number or zero. Okay. There are many examples of parameters that are scalar quantities, including time, speed, energy, distance, and temperature. Okay, so um, when we say a scalar, we're talking about magnitude only, size only, and some properties that we measure that have size or magnitude only are time, speed, energy, distance, and temperature. Okay. A vector, on the other hand, is a quantity that has both magnitude and direction, size and direction. In other words, if you are going to measure a vector property, you must include a direction. Some examples of vector quantities are displacement. And we just saw the example where the displacement was minus five meters, minus 5 meters. So the size is the 5 meters, and the direction was given by the negative sign, which is telling us to the left or west or down, whatever we've established in our reference frame as the opposite of positive. Okay, if I establish to the right is positive, then a negative 5 meters means my displacement is to the left of where I started. Okay, so displacement, velocity, and acceleration are examples of vector properties. And in physics, as well, let me say, in physical science, because the properties that we use to describe a moving object are based on measurement, we can put them in a category. It's either a scalar property or a vector property. Okay. So since a vector has direction, we have to have a way of, visualizing it or drawing it or indicating it, right? We need a symbol to show that it's a vector property. And a lot of times you see that in textbook or examples, they'll use an arrow to represent a vector property. Okay. The reason they use an arrow is because it's very nice to help us. An arrow can point. So whatever the direction of our vector is, that's the direction that our arrow points. And we can make our arrow a certain length according to whatever scale we want to use. And so the length of the arrow tells us the size or magnitude of our vector. Okay. Scalars, because they do not have a direction, cannot be represented by arrows. Okay, so that's notation again, right? Because we all want to be on the same page in terms of notation. So if we're going to be doing one-dimensional motion, as I said, we need a reference frame. Sometimes you hear that referred to as a coordinate system. That is because we're borrowing from the math folk. If you've ever heard the Cartesian coordinate system, we borrow from them to help us deal with our 1D motion because it's simple. It's simple. Just like using an arrow is a simple way to represent a vector, using the coordinate system for 1D motion is a simple construct because we can utilize like a number line to help us. The number line is what? You have a 0 point in the middle, and then on and on forever toward the right, or on and on forever toward the left. And then you can use whatever scale you want to make your markings, right? You can count by ones, you can count by twos, you can count by fives, and then you can attach whatever unit you want to use. If you're trying to specify distance and displacement, then you'll use meters. If you're using this number line for 1D motion to represent velocity or speed, then your units will be different, right? So it's a very easy construct to use, right? So, and when we're working in one dimension, as I mentioned, we can only use what, like forwards or backwards, right or left, up or down. Okay, if we're using the horizontal line, then right is positive, left is negative. Just like you do in a math class, you put the zero in the middle, positive x, negative x, right? If you're using the vertical number line, then we usually use up is positive while down is negative. Okay. All right. Or you can think positive y, negative y. All right. And so we choose these things because it's convenient. All right. Measuring time. If we're going to be utilizing, I mean, if we're going to be describing a moving object, then inevitably we're going to be using the property time to help us do that. So we need to understand this idea of measuring time. And so for example, if the object's position is changing, we want to know how long did it take to go from this point to the wherever it stopped. Or so marking time is important. Okay. And so we use the unit in the metric system for time, the second. Okay. And delta t is referring to how much time elapsed, or sometimes you hear how much time did it take, or how long did it take. Delta t. So we remember that delta means we're taking the final value minus the starting value. Okay. So t final minus t naught. So the final time minus the beginning time. Okay. And as I said, a lot of times we use t naught equals 0 because we say what was the time when our clock was at 0. Okay. So you know, our stopwatch is on 0, and then when the object moves, we start up the stopwatch and keep track of how much time elapsed. All right. And so sometimes, it's convenient to use our starting time as 0. And in that case, if our starting time is 0, then delta t is just equal to t final, or just t. If our starting time is 0, we don't need to distinguish, we don't need to subtract 0 every single time. Just say the delta t is equal to t and leave it at that. I'm not saying we always start our clock at 0, but it's convenient if we do. Okay. All right. So here we go with some additional properties. So if our object is changing its position, inevitably we want to know about the change in position per unit time, or the distance covered per unit time. How far did it go and how long did it take? If we're quantitatively describing our moving object, those are properties that we want to measure. And so the average velocity of an object is defined as its displacement divided by the elapsed time. If you wanted to write it out in the full definition, the average velocity, notice that the average velocity is this script looking V with the bar over it. That bar indicates average. Okay. So the average velocity is the change in time over the change in position over the change in time. Okay. But if we start our clock at 0, we can just use t. We don't have to write delta t, we can just write t. All right. So this average velocity, it is a vector property. It's a vector property. So when you find average velocity, there's going to be a direction involved, a magnitude and a direction. Average speed, on the other hand, is the distance traveled over the time. So average velocity is displacement over time. Average speed is distance divided by time. And it's a scalar.
I'm
Okay?
sorry. Can you repeat that one more time?
Sure. Average velocity is displacement over time. Average speed is distance traveled divided by time. Average velocity is a vector, and average speed is a scalar. Okay. And we'll see an example that I'll work that'll show that the average speed and the average velocity can be very different. Okay. Now, for both of these properties, velocity and speed, or average velocity and average speed, the unit in the metric system, remember we focus on what? SI units, right? SI units, the unit is meters per second, and we abbreviate that M for meters divided by seconds, abbreviated by S, meters per second. So you see, just looking at this particular slide, average velocity is measured in meters per second. Average speed is measured in meters per second. So again, you can't just look at the unit. You have to understand what exactly are you being asked to explain or express or describe for the moving object, okay? Because they're two very different properties, all right? Instantaneous velocity and speed. Now, this is a very interesting, these are two very interesting properties because it's almost like you have to take the time and freeze frame, okay, to get them. So you're saying for instantaneous velocity, what is the velocity at an instant of time, at a particular moment in time, okay? So that's a sometimes a difficult concept to understand, because in our everyday experience, we don't think of stopping time at all. Time just keeps going, right? You know, as a time waits for no man, right? So this idea of freezing time for an instant is sometimes difficult to visualize or conceptualize. But what I like to say is, if you want to think about the difference between instantaneous and average, average looks at an entire trip from start to finish. Instantaneous looks at a particular moment during the trip. Instantaneous is what the cop does you with the radar gun. Gotcha. At a particular moment, when he clocked you, you were speeding. Instantaneous is at a particular moment or instant in time, okay? And if we're talking about instantaneous velocity, remember, velocity is a vector quantity, a vector property that involves size and direction, okay? Now, here's the thing. Because this instantaneous velocity requires a bit of calculus to find it, you know, to calculate it. I don't have you calculating instantaneous velocity. Okay, that's a bit above our pay grade. So if you're going to use instantaneous velocity, it's going to be provided to you. All right. And then its scalar counterpart is instantaneous speed. And so instantaneous speed is a scalar property And what you do is you look at the size of the instantaneous velocity. Remember, size means what? Take off the direction part and focus on the number in the unit, right? Acceleration. So we're kind of moving into these properties now. And so I will say this to you. Acceleration is one of the most butchered properties in all of physical science. When students are being introduced to these properties, acceleration sometimes is very difficult to comprehend. And when students calculate it, they typically mess up the units. There's a big confusion between velocity and acceleration. Please be very careful with that, because what acceleration is doing is looking at how the velocity is changing per unit time. How the velocity is changing per unit time. Okay? So velocity looks at how displacement changes per unit time. Acceleration looks at how velocity changes per unit time. Okay? And you have to think about this. How can I change, change an object's velocity? Well, since velocity has two parts, speed and direction, if I change the object's speed, I accelerate. We know, hit the gas or hit the brakes, you change the speed. Change the object's direction, steer the wheel. Or you could be doing both of those, right? So I can produce an acceleration by changing the object's speed or changing the object's direction, or doing both of those at the same time, okay? I mean, think about if you're driving in your car and you're about to turn a curve, a steep curve. You'll hit the brakes and steer the wheel to navigate that curve. So you'll be changing both speed and direction, okay? All right. Instantaneous acceleration, we don't really calculate that again because that's a calculus kind of thing, but you get the idea. It would be the acceleration at a specific instant. And here is the unit for acceleration: meters per second squared. In the metric system, in the SI system, meters per second per second. So that becomes meters per second squared. Okay. So I tell students, one of the ways you can help yourself with these properties and their SI or metric unit is to get yourself a nice big index card and write down the properties as we come across them, and write down the SI or metric unit that goes along with that property. That way, when you're problem solving or studying, you have the property and its appropriate SI unit right there with you, and feel free to use that anytime you need to, whether it's a homework assignment, a discussion, or an exam. Okay. Acceleration versus deceleration. So, well, we know acceleration in our mind typically means what? We're speeding up, because we say accelerator. We think, a car has you hit the gas, that's the accelerator, right? Well, because acceleration is a vector, it can be positive or negative. It could point in the positive direction, it could point in the negative direction. Okay. And so we have to be careful in our terminology. What I want you to focus on to keep this simple is acceleration positive, hit the gas, speed up. Acceleration negative, hit the brakes, slow down. And we're going to keep it as simple as that. We're not going to look at all these different exotic combinations, like you're moving backwards and hitting the accelerator while you're backing up, for example. We're not going to go there. Acceleration for us is positive. Hit the gas, speed up. Acceleration can be negative. Hit the brakes, slow down. Okay? We'll keep it simple. Now, so we've got the frame of our basic definitions. What is distance? What is displacement? What is speed? What is velocity? What is acceleration? And honestly, those definitions are very broad. And what we often do when we actually have to look at motion is we simplify it. We simplify the motion as much as possible. And so for us to explain, quantify or describe a moving object, we're going to focus on a simple case of constant acceleration. So we take those broad definitions that we just learned, and we're going to reduce them down to a case of constant acceleration. Now, be mindful what that means means the acceleration is fixed. It doesn't mean the speed is fixed. It doesn't mean the velocity is fixed. Because if your acceleration is constant, your velocity is going to change uniformly per unit time, okay? And so we'll be focusing on constant acceleration because it's a much easier lift, if you will, in terms of describing a moving object, okay? And so one common example that we come across when we say that acceleration is constant is this concept of free fall. That is because all objects that are free falling are falling under the influence of gravity only with a constant acceleration of 9.8 meters per second squared down, or if you like to use vector notation, negative 9.8 meters per second squared, okay? So that's one relevant example for constant acceleration. And so if we are going to problem solve, utilize this constant acceleration to help us describe a moving object, we've got a real easy way to do that. And that is because any object that is moving under constant acceleration can be described using these equations. If our object is moving with constant acceleration and we want to describe it kinematically, remember, pure motion, right? Then these equations will help us do it. If it's moving with constant acceleration, we don't need anything else except these equations. Okay? Now, the key is, do you know what these equations are telling you? All right? So these equations are relating distance, velocity, acceleration, and time. I shouldn't say distance, position. Position, velocity, acceleration, and time. Excuse me on that. Okay? And so this first equation allows us to find the object's position. Okay? And you can see that this second equation looks at the object's average velocity. This third equation allows us to find an object's velocity. Okay? This fourth equation also allows us to find the object's position. But notice the difference between this equation and this one. This equation only looks at it from the average velocity perspective. This equation looks at it if the object is accelerating. And then notice this equation, and this equation are connected to time, whereas this very last equation looks at the velocity, looks at the acceleration, looks at the displacement, but there's no time involved. So if you are trying to describe the object kinematically, without utilizing the time involved, you would go to this last equation, okay? So these are what we call the kinematic equations of motion, and we utilize them to describe a moving object that is moving with a constant acceleration. Now, so free fall. So I said that an example of an object moving with constant acceleration is free fall. And so again, on planet Earth, I'm not talking about anywhere else, on planet Earth, we can take the acceleration that the object experiences, the constant acceleration due to gravity, when an object is falling on planet Earth, as 9.8 meters per second squared. We ignore air resistance. And I know that's a big, that's like a big, imagination there, right? Because all your life, you've only ever been exposed to air. So to say all of a sudden there's no air, that's a bit of a stretch. But again, the goal is to what? Look at this motion from the simplest perspective possible, okay? And so when we take these equations of motion here, and what we typically do is replace X with Y, because we typically take X to mean horizontal motion. And we typically take Y to represent vertical motion. And so we replace X with Y, and we replace A with G, okay? Now, be careful here, because they're only talking about the magnitude. Technically, what you're replacing A with in these equations is minus G to represent the fact that gravity pulls down. Since acceleration is a vector, we have to account for the fact that it pulls down. This is only giving the magnitude. But remember, acceleration is a vector. So we replace A with minus G. All right. So what I'll do, I know we're getting close on the time here. Well, actually, on Wednesday, I'll have to, kind of add in looking at the graphical analysis of motion for our object moving in one dimension. And then I'll go ahead and talk about vectors and 2D motion. So I'm a little bit running a little bit behind, but that's because I had the Q&A session right at the start instead of jumping right in. But we need to take a look at how we utilize graphs to help us analyze motion as well. And we'll do that on Wednesday. The thing I want to conclude with, if you'll indulge me, is writing out the kinematic equations of motion for you as they pertain to free fall. Oh, let me see. I didn't want that one. I wanted just my whiteboard, plain whiteboard Fox. Okay. All right. Let's see if that'll work. There, give me a clean one. There we go. So I want to do this for you to help you out a little bit, especially in the problem solving. So indulge me just for a few. Okay. So the equations of motion. And I'm going to focus on the ones that we typically use the most. Okay. So that's X final equals X initial plus V initial T. If you want to know where I end up tell me where I started and how long I maintain my starting velocity. V final equals V initial. Ooh, that's ugly. V initial plus A T. Okay. And then V final squared equals V naught squared plus 2A X final minus X initial. Okay. So these are my equations of motion. So this allows me to figure out my final position, my final velocity, and my final velocity if I don't know any time involved. But let me translate that into free fall. For free fall, A equals, and I'm gonna write it like this so that when you actually put together the equations, they come out. I forgot here. 1/2, sorry, y'all. 1/2 A T squared. I'm looking at that going, something's missing there. All right. So Y final, notice I went from using X to Y, equals Y initial plus V initial T minus 1/2 G T squared. V final equals V initial minus G T. And then V final squared minus V initial squared minus 2, oh, this is equal, I'm sorry, equal minus 2G Y final minus Y initial. Okay, so you can see very clearly here that what we did is substitute. Now our Y is equal X and A is equal to minus G, and we can go from, these are typically horizontal when you're describing horizontal 1D motion. Okay, and why this is free fall. Okay, so if you're utilizing these equations, you can figure out where the object is, how fast it's moving, based on the constant acceleration. So A is constant. Ooh. I'm gonna get this pin down eventually. A is constant. Okay. So that's how you transition your horizontal equations of motion for constant acceleration into free fall motion, vertical motion under the influence of gravity only. All right. So with that, we're just about out of time. We are out of time. So I'll end by asking if you have any questions for me. Just unmute your mic. Feel free to share your question. All right, so I will have this video posted in the next day or so. Sometimes it takes about 24 hours for YouTube to caption the video for me. I'll make it available in the announcements. On Wednesday, we'll take a look at how we use graphs to deal with kinematic motion. We'll look at a little more on vectors and then 2D motion. All right. So if there aren't any questions, we're done. I thank you for your attention this afternoon. I'll see you back here on Wednesday.